Now I want to continue the chapter 3.7 discussion, and number 4 is that what we call a PT1 block. A PT1 block is another word is first order low pass filter. I start with the circuit using the amplifier I have just shown before. We have an input resistance, we have a ground line, virtual ground of the operational amplifier. The input for the resistance is a negative input. We want to assume ideal operational amplifier, and now the change is done in the feedback branch. This is U1, and in the feedback we have a capacitor and in parallel a resistance. So this is the circuit. A note to hide the minus sign out of my equations, I use this direction of my U2. Two resistances, so we need indexes. This is R1, this is R2, this is C. And let's calculate the transfer function of this circuit easily using my shown equation. This minus sign is hidden in the direction of U2. Of course, this is still an inverting amplifier, but in my equation the minus sign is gone. So the transfer function is just the ratio of the impedances Z2, the feedback impedance, divided by input impedance. Input impedance is easy, is R1. Feedback impedance is a parallel circuit of C and R2. There is an equation for parallel circuits, parallel components. If we have this, just this is a repetition from older lectures. If I have a Z1 and Z2 which are parallel connected, this has a new value which is Z1 times Z2 divided by Z1 plus Z2. I think you know this. That is the parallel circuit equation. This I will use here in the case R2 and C. The capacitance impedance, don't forget we have used this, ZC is 1 over PC. The other impedance is R2, so we have now the following equation. Division line of the parallel circuit. Z1 is in our case R2, Z2 is in our case the capacitance, and here we have to add both impedances, and you see this has some division lines. With simplification we get the R2 divided by R1. I want to write into the front, R2 divided by R1. Then I multiply the numerator with PC. Then the numerator, the final numerator, is just 1. And in the denominator of the numerator I multiply with PC, so this becomes a 1. And this becomes R2 times PC, or written in this order P times R times C. And this is the R2 value. Okay, in our PT1 we call this K. Now we have a new parameter named K for this, and we call this the product of resistance with the capacitance is always the time. This is the time constant of my filter. Let's use just the letter T maybe you have heard or learned to use the letter tau. That doesn't matter. So we have the general transfer function of a low pass filter of a PT1 is k divided by 1 plus pt. This is the transfer function of a PT1. Why? Where comes the name? PT1 means that we have a proportional behavior. Proportional means if we have low frequencies, p goes to 0, we have a constant gain k. So with k as DC gain. And then the T1 means we have time constant with only the number of 1. We have 1 time constant. Yeah, if we have 2 of these expressions in series connection, then this is a PT2. If we have 3 of this in series connection, this is a PT3, and so on. So the 1 indicates we have only 1 PT1. One low pass filter, or its first order low pass filter. A 2 means a second order, a 3 means a third order low pass filter. T is the so-called time constant of PT1. Okay, in our discussion, first we calculate the step response. The step response can be calculated always in the same manner. In the frequency domain, the U2 step response is step function with amplitude U sub O multiplied with the transfer function of my system. So k divided by 1 plus pt. And this has to be inverse Laplace transformed into the time domain, back into the time domain to get the time signal of my step response, U2 of t. For this, of course, we need now the relevant row in our table. So I open the workbook, show you the Laplace table, and let's look for the relevant row. We have to convert an expression which has no p in the numerator and a p times a second p, so a p squared in the denominator. So the row indicator here in the first column should start with 0.2. There are some 0.2s, but you see in the second row with 0.2 we exactly have our fitting structure, so we can just copy this element. Yeah, you see here the part of my table O.2.b is exactly this element, but here's a 1 in the numerator, here's the U sub O k in the numerator, so we have to multiply the result also with my constant factor, and then I just copy this time function 1 to the power 1 minus e to the power of minus t over t. Now this is a writing which needs not so many places like this in tables. I prefer the exp expression, but in my handwriting I prefer the e to the power of the exponent writing. Okay, so the this function is a well-known exponential function of a step response of a PT1. I think we have already discussed this. We have done this in chapter 2 or in the beginning of chapter 3. Doesn't matter. We just make a quick drawing of the time function U2 of t. If t is very large, e to the power of infinity is 0. So the final value is just input amplitude times DC gain of my PT1. Then the drawing can be constructed with this tangent construction. Draw a straight line which starts at 0, which crosses the final value at time constant t. Then finally we have one value here. This is the well-known value 0.63 times final value. If you calculate 1 minus e to the power of, if the time t has the value time constant, you see here is a 1, and if you calculate the expression 1 minus e to the power of minus 1, if we do this, we get a value of 0.36. So we have 63% final value reached at one time constant. So here we start with this tangent, and we have this value and reach the final value. The typical values is at 3t and at 5t. At 3t we have here distance less 5%, and at 5t we have here a distance which is less than 1%. So this is the well-known step response of a PT1. I think you have seen in many other lectures. This leads to my symbol of a PT1, which is just the symbolized exponential function. Here we have two parameters, the k and the t. A PT1 is defined with just two numbers. On the top left side we can find the k, and on the top right side we find the t. So, and this defines which type we have. So this is the symbol of PT1. That's the very important filter function. Very often could be found in sensors. Sensor behavior is very easy identified with the PT1 structure, or simple inertias like motor behavior fits very good to a PT1 filter function. So this very often can be found in control system discussions. I want to finalize the PT1 discussion with the Bode plot. The Bode plot is the drawing in logarithmic scaling of the complex frequency response. So we have to convert the transfer function in the frequency response by just replacing all p's with j omega. In our case we have only one p, so we have the complex frequency response is k divided by 1 plus j omega t. We need the magnitude function. The magnitude function can easily be drawn, calculated by knowing what I have mentioned in the last one of the last videos, that the magnitude of a ratio is the magnitude of the numerator divided by the magnitude of the denominator. So here we can write magnitude of the numerator is still our k, and the magnitude of the denominator is calculated with Pythagoras square root of real part squared plus imaginary part squared plus omega t squared. And the phase of the PT1 is the phase of the numerator is 0 minus the phase of the denominator is arc tangent the imaginary part divided by the real part. Imaginary part is omega t and the real part is 1. So this is the simple phase equation, and we want to draw now first the magnitude curve, and then after this we want to draw the phase curve in a logarithmic scaling. So start with the sketch diagram of the magnitude curve. I indicate the logarithmic scaling with indicating that f magnitude is then drawn in dB. Then we have a horizontal axis with the logarithmic value of omega. Note this is the logarithmic function to the base of 10. We should look for two approximations f omega. First, what happens if we have very small frequencies? Small means small is if this is very small, so if omega is very small compared with the 1 over t factor, or omega t is small compared with 1. If we have this case, then we can say the approximation of the magnitude, if this is very small compared with 1, and this is squared, small number squared is much smaller, so I can neglect this compared with the 1. Now this is large, so I make approximations, very simple with the principle. If I have a sum, and one part of the sum is large or small, I can neglect the small one. If this is very small, I can neglect this, and the 1 is that what remains. And you see, square root of 1 is 1, k divided by 1 is k, so we have just a constant factor k. So for very small frequencies, we have a constant line, and still in the region of 1 over t, this is not anymore true. Then we can draw this curve, and the distance to 0 dB is k in dB. Don't forget to convert the k value into a dB value. Yeah, don't forget it. Otherwise you get a wrong drawing. The same we can do for the high frequency case. If omega is very large compared with 1 over t, then we can say, okay, in this case, we can neglect the 1. Now, if this is very large, say 1000 squared 1 million, and we add a 1, then this is a very small change, so we can neglect the 1 if this is very large. Then we can apply the square root function. This removes the square function, and we have just simple the function k divided by omega t. Okay, this is for large frequencies. That's what we know already from the integrator. The integrator has exactly this function. So 1 over omega is nothing else in a double logarithmic diagram, a straight line curve, which is of course not anymore valid if this is not true. So we have a curve with minus 20 dB over decayed gradient. The question is, can we find now a point so that we can draw this, but the position of this gradient should be defined. One point could be this value, crossing of 0 dB, but there will be a better point. The better point is exactly this point. That is the point where the low frequency approximation, we call this asymptote, it crosses the high frequency approximation, also called the asymptote. Yeah, called asymptote. So this is an asymptotical construction. We have here an asymptote, here an asymptote. The crossing point is interesting. That is that point where this is equal this. Now this is a low frequency asymptotical curve, high frequency asymptotical curve. The cross point is that where omega and z value where both is equal. This is the case if omega is 1. So let's calculate. And we can say, okay, if we have omega value is 1 over t, both curves are crossing. Now I want to have the value at cross point, the correct value. This is the asymptotical cross point is exactly at k, but the correct value should be calculated correctly. F at cross point of asymptotes is how large? Is k divided by if omega is 1 over t, then this is 1. Squared is still 1. 1 plus 1 is 2. So this is k divided by a factor of 2. K divided by the square root of 2 is, say, 0.7071 times k. Or in logarithmic values, if I calculate 20 dB times log value of 1 divided by square root 2, do this with your handheld calculator, then you get very accurately 3 dB. Yeah. Sorry, of course I have made a mistake. This must be a minus 3 dB. Let's just show this in the handheld calculator. I have the 2, then I want to have the square root function is 1.414. Then I have the inverse 0.7. I calculate the logarithmic factor and multiply with 20. And then you see negative 3.010 dB. So the difference to the real 3 dB value with which we calculate is very small. It's less than 0.3%. So we have a 3 dB point. You can say, okay, the correct value, let's draw the exact curve. Correct curve starts here, of course, with identical behavior like my asymptotes. Here's a red curve. The position here, we have a point, just calculated. The difference to the corner point is minus 3 dB. So this curve can be drawn manually in this way. This is the red is the exact magnitude curve. If we want to have more points here, there is another interesting point. Say here, if we go 1 octave deeper to 1 divided by 2t, this is an octave. Octave in frequency is a factor 2. Come from music, the octave. If you measure the frequencies of two tones which have a distance of 1 octave, you can easily find that then the frequencies have the factor of 2. So if I go 1 octave deeper, this point then differs from the asymptotical curve very near to 1 dB. Same as if you go 1 octave higher, it's the same distance here. 1 octave higher, you can show, not here, but you can believe me, this is also a distance between the asymptotical curve and the correct curve, which is very near to 1 dB. Okay, with this, you see we have a very accurate drawing of the Bode plot in all details. What happens, last question, what happens if we change k in green? Ja? Das sieht nicht gut aus. So, again. Change of k and t. If k changes, then, and this point is the same, you see the curve is just shifted up and down without changing the shape of the curve, because the gradient is always the same, this position is the same, so the curve just moves up and down. If we change t and k is constant, this distance is the same, but then this point runs to the left or right side. So we can say this curve changes the position in the horizontal version if t is changed. So what we can say, the shape of the curve is always independent of k and t. Now, you can say shape of curve is independent of k and t. So all PT1s in the world have the same shape, the same magnitude curve. If the scaling, of course, if the scaling is the same, then with the same scaling, all PT1s in the world have the same magnitude curve, only the position, but horizontally is defined with t, vertically is defined with k. The same is valid for the phase curve. Very quick discussion for the phase curve. The phase curve of a PT1 is completely negative. It starts with 0, that is the negative arctangent function. Small omegas give a 0 value, large omegas gives a value which approach the minus 90 degree value. We can say at 1 over t we have the value of negative 45 degree, and the phase curve looks similar to this. Here we have a decrease and then approaching the final value. This curve has a symmetry point here, as a symmetrical behavior in a logarithmic diagram. One word to this 1 over t frequency, the radian frequency omega with the value 1 over t is called corner frequency, just for the reason that the asymptotical curves have there a corner. That is the reason for the name corner frequency. Note that omega c is the inverse of the time constant without 2 pi, because the time constant has nothing to do with the period of the sinusoidal signal. Yeah, of course, then if this is the frequency, we have to divide by 2 pi to get the radian frequency. In our case, we have just simple, the inverse of the time constant is the corner frequency that just comes out of our discussion here. If I change k and t, then you will see the following effect. If k is changed, nothing happened because the k has no influence to any phase value. If the t is changed, then the curve is shifted to the right or left side. So the position, the position of the curve depends on the corner frequency, depends on the time constant t. That's all. All PT1s in the world have the same shape of the phase curve. So far, all to the PT1.